All right, guys, we are now at my absolute favorite part of the class. In fact, actually, I'm very, very stoked to even be able to just record this and so that you guys can actually have this to look at it anytime that you need. Once we've gone past test 2 material, in which we've looked through chapter 3 and chapter 4, gone through determining systematic processes that we can utilize in order to find voltages or currents across or through a resistor, and then also the ways that we found that we could manipulate the circuit in chapter 4, looking at superposition, looking at source transformation, as well as Thevenin's equivalent. We're now in the section of the class where we start talking about energy storing elements, and specifically capacitors and inductors. Everything that we have been working with up until this point have been simply resistive techniques and resistive circuits. And those are fantastic in order to really start determining and developing a foundation for electrical engineering principles. But resistive circuits are essentially, for lack of a better phrase, child's play. And now we're actually starting to work with elements in which we actually start seeing some very, very unique things happen. And the first element that I really want to talk about is essentially one of my favorites. It's the capacitor. And the capacitor, most of you have been dealing with, you just don't really realize that you have actually dealt with the capacitor in the past. The easiest example of the use of a capacitor is back when we had disposable cameras, or basically any type of film camera in which we had to utilize a flash. And before you could actually take a picture with that or utilize that flash, you'd press the shutter button halfway down, and when you did, you would actually hear this whirling sound. And basically it would increase in terms of tone and pitch, and eventually that pitch would just kind of level out, and at that time you knew that you were able to press the button fully down, the shutter would close and the flash would go off, and then you would actually snap a picture at night. What's actually really happening during that time you hear that whirling sound is that you're actually charging up a capacitor. And then once you actually charge the capacitor and becomes saturated with enough charge, then you actually utilize that stored energy for the flash, in which it's all dumped across basically a flash, in which flash goes off, and then we actually have to clear red eye within the picture. But what is this energy storing element? How do we actually develop a model for that? That just in the same way that we had a model for the resistor with Ohm's law, how can we actually determine ways that we can actually solve these circuits? And the key with these elements is that their interconnection forms essentially differential equations. And in this class, since all of you are likely taking differential equations right now, we're actually going to develop a method so that you can actually solve for these systems kind of in a roundabout way without actually solving differential equations traditionally with Laplace transformations. That's what we do within circuits too. Within this class, we're actually going to go through and determine exactly what that model is, what the model actually means, and we're going to, or at least I'm going to develop the generalized solution for you guys for a first order resistive capacitive circuit, and then later on resistive inductive circuit, and also for second order systems. But you will not actually have to solve the differential equation outright. We'll worry about that later, especially since you guys are in differential equations right now and learning how to solve these systems up front. So what is a capacitor? Well, in simple terms, a capacitor is it's an energy storing element that simply allows for us to store positive and negative charge on essentially what we have is two plates. And these plates are actually separated a very, very specific distance. And between those two plates, we actually have something called a dielectric. And a dielectric is usually either a film or an oil, or sometimes even just air, in which we actually just allow for basically those two plates to be separated with the substance that sits in between. And that dielectric basically allows essentially for the flow of what we call an electric field. And within this element, it basically works off of the flow of the electric field itself. Now, what really happens here is that essentially when we allow current to flow to this element, essentially positive charge and negative charge, in which the top plate where the positive charge collects, we call that an anode, and on the bottom plate we call that a cathode, and that's what collects the negative charge. As current flows, basically we allow for the build of positive charge on the anode, negative charge on the cathode, and as that happens we actually build an electric field in between those plates and then actually surrounding those plates. And as that happens, we actually start storing this potential difference, or essentially we start creating a voltage to be stored across those two plates with the building of this electric field. And the capacitor is pretty unique, and also, in fact, it was awarded the unit of Farad for essentially the godfather of electrical engineering, Michael Faraday. And 1 farad is essentially equal to 1 coulomb per volt, or Q is equal to C times V. But the capacitance, what is capacitance? Well, capacitance is essentially the ability for it to store charge. That's the ability for the element to store charge, and that's equal to the permeativity of basically that dielectric multiplied by its cross-sectional area and then divided by the distance. So essentially the more area that we have, the more ability that we have to store charge on those plates. However, as soon as we actually start increasing the distance between those two plates, that means that electric field has further to actually travel and essentially decreases our ability to actually store charge. So again, within the 3 main portions of this element that allows us to determine a value of capacitance is essentially the area of the plate, the permeativity of the dielectric, and essentially what that is the resistance that dielectric has in forming that electric field. And then finally, with the distance between the plates, that actually kind of helps us understand also and helps us reason the ability to determine that capacitive value. But once again, when we consider that current actually flows to this plate and that positive charge builds and that negative charge builds, and that's due to this fact that we're building this electric field in between and then surrounding those plates, we actually start coming to the conclusion that essentially what we're looking at is a very dynamic element. And when I say dynamic, it means that we're starting to introduce change within the circuit. And that change is very unique in terms of how basically that positive and negative charge actually builds. And in fact, actually, for the capacitor, the current is actually dependent upon that voltage changing between those two plates. Now, one of the things I always want my students to actually understand is that this is when we really stop looking at an equation specifically and just saying, oh yeah, current, that's just equal to C times the derivative of the voltage. Yeah, that's cool. We have to know the actual skill set of taking the derivative within basically a mathematical equation, but we also have to have the ability to look at the equation and actually reason it and intuitively understand what it's actually trying to model. Remember, guys, that mathematics does nothing more for us than basically model a physical concept. It just gives it a very, very specific language. And what this equation, which is in fact actually a first order differential equation, what this is actually trying to tell us is that current is dependent upon that change in the voltage. So as long as that voltage is actually changing, or in other words, as long as that charge is building on the anode and cathode, or actually decaying, leaving those plates, then we actually have a current. And when we actually don't have any change, then we actually get essentially 0 amps, or what really happens is that capacitor starts acting as what we call an open circuit. No current can flow. But how does this element relate in terms of resistance within the circuit? And how do we actually develop a solution for such a type of system? Now, what we're going to be looking at essentially for this portion of the class are first order differential equations, first order dynamic circuits, circuits that have the ability to change over time. And that's why we actually start utilizing the differential equation, is because we're modeling change with respect to time. So let's move over to the other side of the board here. All right. So in order for us to actually derive a type of solution for the voltage across a capacitor, because obviously if we see that what we call its current voltage characteristic, current is equal to C times dVt dt, then that's actually a differential equation in reference to the current. But what would be the solution to the voltage across that capacitor? And how we actually determine a solution in which we actually could see what that time varying response for that voltage would actually be. Well, let's take a look at a very, very simple circuit here, in which we have a capacitor as well as basically a resistor in parallel with each other. And essentially what we have here is what we call a source-free resistive capacitive circuit, or RC circuit. So essentially, going back to the discussion about the camera flash example, once we actually click that shutter button, we actually do create a source-free RC circuit in which we actually would have to go back and recharge that capacitor. But what we're doing is dumping all that energy. We're allowing for the capacitor to dissipate that energy through essentially a resistive element, which in this case is obviously going to be our flash. But usually with a capacitor, we always can say whether it has essentially an initial condition for that voltage across it. Sometimes we have an initial voltage, sometimes we don't. In the camera flash example, sure enough, there is a voltage that we store across those two plates. So let's see if we can actually determine a solution for this differential equation and see if maybe we can actually determine what the voltage is across this element. Well, we have two elements in parallel, and elements in parallel obviously have different currents flowing through them, but they have the same voltage. Obviously have the same voltage. So in this case, if they're parallel, then they actually share that same voltage value, or in this case, it's actually going to be time varying, but their currents are different. The current flowing through that capacitor is definitely going to be different than the current that flows through that resistor. So we can apply Kirchhoff's current law, KCL. And by KCL, we actually see that IC of t plus IR of t, in this case, is equal to 0. And it's equal to 0 because at this point, there is absolutely no separate excitation that's actually being delivered, that is delivering energy to these two elements. So essentially, what's going to happen if there's no separate excitation, what we're going to see is that capacitor is going to dissipate it's all of its initial charge stored in the anode and the cathode and just dump that right into the resistor. And why it's actually going to lose its energy, essentially we're going to see it's going to die out to 0, is also kind of unique as well. What does the resistor do? Well, it takes energy to actually push that current through it and converts that into heat. Eventually it dies out. Well, let's take a look at this KCL equation. Now, we said that the current voltage characteristic for IC of t is actually C dVt dt, or basically the capacitance multiplied by the change in that voltage with respect to time. But if we look at IR of t just by a rearranging of Ohm's law, then V of t divided by R is in fact actually equal to IR of t. Now, one thing before I go any further that I want to note is, note right now that we're saying IC of t, IR of t, instead of just saying IC or IR. And the reason why I'm saying this and denoting a t within here, or time with respect to that current, is because now we're looking at time varying responses. So with strictly resistive circuits, everything that happens within a circuit is near instantaneous. As soon as we turn on the source, we have near instantaneous current, and we have near instantaneous voltage applied wherever in the circuit. But now we're talking about time variance, and so we actually have to denote that time variance is actually going to be with respect to IC of t or IR of t or even a V of t for the case of two parallel elements that share that same voltage. So if we look down here, guys, well, we got C dVt dt plus V of t divided by R, and that's equal to 0. Congratulations, we got a differential equation. Bam, right there. C dVt dt plus V of t divided by R. But this we actually cannot solve yet because we do not have basically this differential equation in terms of its standard form, or since it's equal to 0, we could actually say homogeneous. But if we divide through by C and isolate that highest order derivative, then we get dVt dt plus V of t divided by RC, and that's actually equal to 0. If we rearrange that equation though, see this is where it may be a little bit different. Looks like here, if I rearrange that equation, dVt divided by V of t is equal to negative 1 over RC. If I move that over and then just divide through, how does that work? Well, all this derivative actually says is the change in the voltage with respect to the change in the time. So, when we think of a derivative and breaking up those portions, remember a derivative is an operative function. And in this case, if we break up those portions, then we're actually saying the change in the voltage divided by that voltage. And that would actually be equal to 1 over RC dt, or the change in time. So, once we actually have the equation in this form, we can actually integrate both sides. What easier way to get rid of a derivative than by integrating it? And get rid of that change by actually seeing what the integral would be for that. But in this case, how do we actually determine what type of integral that we actually want to work with? Well, when we consider the definite integral, we normally would say from negative infinity up until some specific point in time. But in this case, and I'll explain this why in just a bit, there's no reason to actually denote negative infinity here because we actually know what everything is going to be before t is equal to 0. We'll talk about that timeline in a bit as well. So we say V naught, we integrate with respect from V naught to V of t times 1 over V dV, and then we integrate from 0 to t of negative 1 over RC dt. And once we do that, we can actually look at these integrals. We know on the right side that if we integrate this form right here, then we actually get a result of negative t divided by RC. Over here though, just integrating that we could apply maybe a logarithmic identity. And that logarithmic identity may actually help us further solve this problem. So the logarithmic identity that we could apply for this definite integral here actually comes out to be equal to the natural log of V of t minus the natural log of that initial condition, which is actually V naught. So once we do that, we can actually apply another logarithmic identity that relates to basically two logarithms, or natural logs that are actually being subtracted off of each other. And sure enough, we could say the natural log of V of t divided by that initial condition of V naught is in fact equal to negative t divided by RC. Oh, well, how do we get rid of a natural log? Let's take the exponential of both sides, see what we get. If we raise the natural log of V of t divided by V naught by its exponential, and then over on the other side, that's going to be equal to the exponential of negative t divided by RC. Then in fact, actually, we get rid of the natural log and we're left with V of t divided by the initial condition of V naught. And here we get, that's equal to the exponential of negative t divided by RC. And sure enough, if we multiply through by V naught, V of t comes out to be equal to V naught times the exponential of negative T divided by RC. Guys, this is the solution to a first order differential equation here. In this case, especially if it's source free and does not have a final condition in the instance that that voltage actually dies out. And what we see here is that we have an exponential form. And guys, this exponential form accurately models what's actually going on within that system. All the guys here in my lab, and I'm going to show you an example of this because essentially we're not going to have lab for the rest of this semester, is that we actually do come out and measure this, and we see how this works within a real case scenario. But here, the portions of this equation are very, very unique to us as well, because we got not only this initial condition, which is a coefficient of that exponential, because the exponential has got to start somewhere. But RC right here is actually what we call a time constant that kind of helps us understand the rate at which that voltage is either going to decay, or if that voltage is actually rising, then it gives us more of an understanding of what's really going on in that circuit. And it's dependent upon the resistance that's seen by that capacitor, and also that capacitor's ability to actually hold charge. So I've kind of said a lot of things here in terms of not only the derivation, but also of the function of the capacitor itself. But before we can actually take something like a differential equation and then start utilizing this form of the solution to actually start solving problems, we need to understand also what's really happening within a dynamic system, and also essentially what we consider as the timeline of that system. So here I actually mentioned about an initial condition. What does the initial condition mean? Well, within a dynamic system, we usually consider that that system has been sitting there and has a steady value. And then we actually invoke a change, a physical change within the circuit that actually causes for that change to actually be excited. So let's look at the timeline. Let's move over one board. All right. So we derived here that the time varying voltage in a source free circuit, that a voltage would be for across basically that capacitor, is dependent upon that initial condition that was actually built across that capacitor. Well, e to the negative t divided by RC means that it's actually going to decay in nature. So we start off at its initial condition. Because this is source free, there's no other source to excite a voltage across that element, then we actually decay out to zero and it dies. All that energy is actually going to be released into the circuit and then actually cycles through, and then as we actually perform work in order to get that current through that resistor just converts it into heat, and eventually all the energy that was stored amongst that electric field within that capacitor actually essentially just dies off, and there's nothing left. There's no energy left to be expended that actually gets that charge through that element, and so we basically just die off. Now, I mentioned something called the time constant just a bit ago. What is a time constant? Well, this little guy right here, negative t divided by RC. Well, 1 over RC, as you guys will actually see in differential equations, is actually the root of the characteristic equation of that differential equation itself, in this case the first order. But RC itself is actually something also very, very unique for us, and it actually kind of tells us a major portion of the decay itself, and kind of like the rate at which it's almost decaying. And I don't like saying rate sometimes because obviously that's with respect to time. This is a actually specific measurement of time here, where tau is equal to r times c, or actually we're going to see it's r Thevenin times c when I start doing problems for this. But that time constant essentially just tells us the time period at which we've actually decayed off all the way down to 0.368 of that initial value, or essentially the majority of that voltage is actually decayed off. Now, 0.368 of that initial value, or 37% of that initial value, where does that come from? Well, this is V of t is equal to V naught times e to the negative t divided by RC is a time varying equation. If we evaluate that equation at t is equal to RC, which is in fact actually measured in time, then if we denote that the voltage is, that equation is evaluated at RC, then V naught times e to the negative RC divided by the time constant actually gives us V naught times e to the negative 1, and you should punch this in on your calculator just to make sure you see it. The e to the negative 1 comes out to be 0.368 of V naught, or in fact actually 36.8% of that initial value, which is where we see the majority of that voltage die off. And the portion at which, the final tail end of that portion at which we actually see the remainder of that voltage decay takes a little bit longer, and it's definitely not as quick as what we see with the time of the resistive value multiplied by the capacitance. But this timeline that I mentioned in dynamic analysis, in a dynamic system, what is that timeline and what does it mean for us? Well, a couple of things. Anytime we actually evoke a change in the circuit, we always start off and say that happens at t equals 0. And the reason why we say t equals 0 is because we always know that the circuit was actually sitting at some steady state value in which it's just hanging out there. That voltage charged up for basically that positive and negative charge across those two plates, and essentially just it's hanging out. It's just sitting there. It's saturated with charge. Doesn't have any current flowing through it because the change in voltage went away, so therefore the current goes away. So it's sitting there in a steady state. It's not changing. It's not changing at all. However, if we change the physical schematic or the physical circuit itself, we do invoke a change, because every steady value that's within that circuit is dependent upon that circuit sitting there as is. But when we change that schematic, when we change the circuit, then we actually change the values that are actually driving that response for that voltage across the capacitor. So that's when we say at t equals 0, some event happens. And usually that event that happens is either a switch opening or closing within the circuit. And when we do that, we change the circuit and therefore create a temporary period in which we're actually seeing, or what we call t greater than 0, is actually when the circuit is going through its dynamic state and actually changing. And it's not permanent, it's just changing right here. Going through that exponential. That exponential represents a dynamic change that's actually happening within the circuit. T less than 0, we were in steady state. We invoke a change into the circuit. Bam! Here we go. T greater than 0, we're going through transient period, a temporary period in which eventually, just like chaos theory, everything just levels off and the circuit regains another steady state. In the case of what we just looked at for a source-free RC circuit, that steady state is in fact 0. For other cases, as in when we actually charge that capacitor for the flash, that steady state before we actually press that button all the way down actually gave us a full value of voltage across that capacitor. And we say t equals infinity here as a model. And I remember a student asked me years ago, when we say t equals infinity, do we actually mean the end of time? No. There's no capacitor that would be seen and floating off in the space that would actually be charged with respect to the Earth blowing up and the end of time as we know it. No, this just is just another model for us that says that the circuit has been sitting there long enough to gain a steady condition. And so we actually denote a final condition for the voltage across the capacitor, whether it's charged or not, as actually regaining a steady state. So once again, t less than 0 represents the initial steady state that we're looking at. T equals 0, we invoke a change. During this t greater than 0 or transient period that we're looking at, we're seeing the change actually occur. And then here, t is equal to infinity, we actually have the steady state regained. What we are actually looking here, guys, is actually what we call a total response for the voltage across the capacitor, and the solution to that voltage across the capacitor after solving the differential equation is actually complete and actually models every bit of this. So the total response, if we actually consider that we would have potentially a final solution for the voltage across the capacitor that would be of a scalar value almost, then we actually say V of t is not only just equal to V naught times e to the negative t divided by RC, but also V infinity plus, in parentheses, the coefficient of the exponential of V naught minus V infinity multiplied times e to the negative t divided by what we call tau, or time constant, which is equal to R Thevenin times C. Guys, that is the absolute full response that we have. And this is actually the only equation you guys actually need to know. And within the work that we're going to be doing in Chapter 7 and then later on in 8, I've actually already solved the differential equation for you. Only thing you guys are going to have to do is find an initial voltage, final voltage, and equate resistance to that capacitor. Because it's that resistance that the capacitor sees that's what's going to